specimen is essentially elastic. After a stress called the elastic limit is reached, the deformation is mostly plastic. Unlike elastic deformation, plastic deformation can be very large. It is not recovered when the load is removed, and it is time-dependent. The atomic mechanisms responsible for elastic and plastic deformation will now be examined. The mechanism of elastic deformation can be appreciated by representing two adjacent atoms as spheres, with their centers joined by a spring, which represents the interatomic bond. As a uniaxial tensile stress is applied, the spheres move apart and the spring is extended. The strain varies linearly with the applied stress, and the ratio of the stress to the strain in the axial direction is the elastic modulus. The stiffer the spring, which corresponds to stronger bonding, the larger will be the elastic modulus. Now consider a hexagonal close-packed unit cell. Only a few of the bonds are represented as springs to avoid confusion. As stress is applied, bonds in the direction of the applied stress are stretched, while bonds mainly transverse to the applied stress are compressed. Therefore, the specimen dimensions increase in the longitudinal direction and decrease in the transverse direction. When the stress is removed, the strain, called elastic strain, is recovered. When the specimen is subjected to larger stresses, the atoms eventually slip past each other. They are seen slipping on a basal plane. This slip is plastic deformation. When the load is removed, this strain is not recovered. The tensile specimen shown deforming is a zinc single crystal, which has a hexagonal close-packed crystal structure. This view is in the direction of slip. Note that the width does not decrease as the specimen elongates.
If the deformation is observed from the side, the slip direction is in the plane of view and can be readily seen. Note that in this orientation, the width decreases as the specimen elongates. The offsets produced on the surface when adjacent regions slide past each other appear as lines and are called slip lines. Actually, as can be seen by magnifying a portion of the surface, slip usually occurs on a number of planes in a narrow region. These slips are of closely packed groups of slip lines. The offsets at the surface are about 2,000 angstroms, while the distance between slip lines is about 200 angstroms.
Evidence of slip can also be seen on the surface of polycrystalline specimens that have been polished prior to deformation, such as this polycrystalline zinc specimen, which was shown being deformed. When observed under a microscope at a magnification of 3,600 times, slip lines can be observed. Note that these slip lines are parallel within grains, but discontinuous across grain boundaries. This is because slip occurs on specific planes in specific directions. For example, consider the hexagonal close-packed structure of the zinc single crystal. Slip occurs on a basal plane in a close-packed direction. This can be appreciated better when it is seen with several adjacent unit cells added. Atomic planes lying just above and just below the slip plane, viewed from above, readily illustrate the slip direction. When viewed from the side, the comparison of two rows of close-packed atoms with two rows of non-close-packed atoms show why slip occurs more easily on the close-packed planes in the close-packed direction. The force needed can be related to sloping lines tangent to the atoms. These sloping lines are in the direction of the initial atom movements for slip. The steeper the slope, the larger the stress required for slip. Therefore, slip is more difficult to induce on non-close packed planes. Observe what happens when a single crystal of zinc, oriented with the basal plane perpendicular to the applied stress, is subjected to tension. Rather than slipping on some other plane, the specimen fractures on the basal plane. Only elastic strain occurs. The resulting fracture surface is smooth and has a mirror-like finish. Plane of atoms over an adjacent plane. This deformation behavior is called slip and is the predominant mode of deformation. If the behavior of one of these planes is examined schematically by looking at a model of crystalline material, and the upper half of the model is moved one atomic unit to the right, the bonds of many atom pairs must be severed and rejoined. This action results in the formation of a slip step of one atomic unit at the material surface. For a macroscopically large piece of material, the energy required to stretch every bond in this single plane to the breaking point is the product of the energy of a single bond pair times the total number of atomic bonds across the plane. It is known, however, that the actual energy required to create plastic deformation is only 1/10 to 1/100th of the theoretical bond strength of the material. Observe how this is possible. If the top half of the crystal model is removed to reveal one surface of a slip plane, the rows of atoms in this plane are seen to be dislocated or rearranged from the uniform pattern one might expect to find. A crystal actually contains a large number of such crystal lattice defects known as dislocations. When the atoms contained in one surface of a slip plane are dislocated in this fashion, while the atoms in the opposite surface of a slip plane are dislocated in a reverse fashion, an area is formed in which atoms from both faces are clearly misaligned. This region is referred to as a dislocation loop. If a portion of the top half of the crystal is replaced and a portion of the lower half is removed, the resultant cross-section clearly demonstrates that a dislocation is nothing more than a localized rearrangement of atoms, such that not all the atoms above the slip plane are joined to their counterparts below the slip plane. In one region, the structure is equivalent to an extra half plane of atoms in the crystal above the slip plane, while in another region, there is an extra half plane of atoms in the crystal structure below the slip plane. These are known as edge dislocations. If that portion of the crystal lying above the slip plane is once again removed, and the dislocation loop is followed to a region 90 degrees from an edge dislocation, it is evident that on the slip plane, the structure is equivalent to having sheared adjacent atoms. The layers of atoms above and below the slip plane have thus formed a screw dislocation. At regions on the loop lying between the edge and the screw dislocations, the structure is a combination of the two and is known as a mixed dislocation structure. It should be emphasized that only the atoms in the dislocation are disordered, and that the atomic order remains unchanged everywhere else in the crystal. If one examines a cross-section of one quadrant of the crystal model, it is clear that by applying enough stress to the rows of atoms lying above and below the slip plane, a point can eventually be reached where the attractive force of the next nearest neighboring atom in the lower part of the slip plane is greater than that of the nearest atom. When this occurs, the first line of upper atoms will join the second line of lower atoms. At the same time, the second line of upper atoms will become inserted into the space between the second and third lines of lower atoms. Thus, deformation can be induced in an otherwise perfect crystal by applying a shear stress and breaking only a single line of atomic bonds, a process which takes only a fraction of the force or energy required to break all the bonds in a single plane in the crystal. If one continues to apply a large enough shear stress, single lines of bonds will continue to break, and the lines of atoms in the upper half of the crystal will be joined to the successive lines in the lower half. This process will expand the dislocation loop until it runs out of the crystal at each end. When this occurs, a step of 1 atomic unit is left at each end of the crystal. Permanent deformation has occurred by breaking only a fraction of the total number of atomic bonds in the slip plane at any one time. This motion is analogous to the forward motion of a caterpillar. Note that in order for the caterpillar to move, he first moves his rear legs forward, creating a hump in the middle of his body, so that only a few of his feet are off the surface. This hump is equivalent to the dislocation introduced into the crystal. If the caterpillar moves only a few pairs of legs at one time, he can move his entire body forward by 1 unit, equal to the distance between leg pairs, and expend only a fraction of the energy which would be required to move his whole body at one time. In a similar way, because of internal defects in crystalline materials, the force required to create plastic deformation by a successive breaking and rejoining of atomic bonds is much less than the force required to break all the bonds in a crystal simultaneously.
Junction are coated with a thin layer of zinc. If we look closely at the surface of the zinc, we see it's built up of many different patches. You can find this effect on a number of zinc-coated objects. The patches you see are crystals or grains of zinc. Here's a piece of a different metal. It's been machined along one edge. You can't see any grains in this surface. However, if we turn it over, it's quite a different story. This piece of metal has been broken in half. Along the broken edge, you can see some of the grains from which this material is made. All metals are made up of grains, although you'll rarely see them like this. In fact, with most metals, including this piece of aluminium, the grains aren't visible, not even on the surface. Here's a way of making them visible. First, we must give the aluminium a mirror-like finish. And there we are. Next, we treat the carefully prepared surface with a very powerful acid. Gloves are essential for this operation. As soon as the acid's had time to react, the metal must be washed. It's then given a second treatment with another special chemical. We call this process etching. The particular chemicals used depend on the metal we're trying to etch. One final wash, and there are the grains. Grains of pure aluminium. They're all similar, both in size and in structure. They appear as different shades only because of the way they reflect the light. By etching, we can reveal the grain structure of any metal. Here's a different sample of aluminium. In this case, the grains are much larger and they vary in size. And here's a piece of copper. In this sample, the grains seem to get smaller as you get nearer the middle. Zinc, a sample whose grains are all shapes and sizes. But how do grains form? To find out, we've gone back to the stage when a metal is molten. In this furnace, the metal is aluminium. When the time is right, the furnace is tapped. The molten metal runs out along channels into molds to form huge slabs of aluminium. In turn, the solid slabs will be rolled into sheets. From time to time, a small sample of the molten aluminium is taken for analysis. metal is poured into a mold and left to solidify. Now we can see what happens as the aluminium solidifies in a special film. At a number of points in the liquid metal, tiny crystals begin to form and grow. Each crystal grows outwards in all directions until it meets the surfaces of its neighboring crystals. In engineering terms, each fully grown crystal is called a grain. In this piece of solid aluminium, there's a very large number of grains. Now, once the aluminium's been cast into slabs, it's rolled into sheets. To get the metal down to this thickness, it's been rolled many times. It's now relatively cold, so as the metal is squashed between the rollers, it's being cold worked. Let's find out what effect the cold working has on the grain structure of the aluminium. Here we're etching a piece of the aluminium before cold working. At this stage, the grains are all approximately the same size and the same shape. Remember, they appear different shades only because of the way they reflect the light. Now we'll cold roll a similar piece of the same aluminium.